Welcome to my presentation on Boruvka's algorithm. Boruvka's algorithm solves one of the most well-known problems in the field of computer science, finding the minimum spanning tree of a graph. In this presentation, I will give an overview of the algorithm, explaining its principles. We will review the pseudocode for Boruvka's algorithm, and I will give you a demonstration of my Java implementation. Finally, we will discuss applications of the algorithm. Firstly, to understand what a minimum spanning tree is, let's review what a spanning tree is. The spanning tree of a graph G is a subgraph of G which contains all of its vertices, and it is a tree, thus there are no cycles. Below we see the graph G with 4 vertices. The following 3 subgraphs are spanning trees of G which connect all 4 vertices. To find the minimum spanning tree of a graph, the graph must be undirected, connected, and weighted. Undirected means the edges are bidirectional. Connected means there is a path between every pair of vertices, and weighted means each edge has a weight. It is important to note that the weights must be distinct. The minimum spanning tree is a spanning tree of the graph G, where the total sum of the weights of the edges is no larger than the total weight of any other spanning tree of the graph. Below is graph X. This is the MST of the graph. The edges colored in green produce the minimum total weight of the edges. Boruvka published the first algorithm to solve the MST problem. To find the MST in a graph, Boruvka's algorithm takes a greedy approach, making the locally optimal choice at each stage. The algorithm takes input of an undirected, connected, weighted graph, and then conducts steps known as Boruvka steps to find the MST. The algorithm is based on the principle that the lowest weight edge of each vertex must be a member of the MST. In the first Boruvka step, the algorithm treats all vertices as their own individual trees, and locates the least cost edge incident to each vertex. These edges are all added to the forest, where a forest is a collection of trees. The algorithm then now finds the lowest cost edge from each previously constructed tree to a different tree. This process is repeated, where in each iteration the number of trees are reduced until the result is a single tree. This is the MST. Below is a graph A, B, C, D, E. The algorithm analyzes each vertex and locates the least cost edge. Figure 2 shows a selection of these edges to create 2 trees, D, A, B, and C, E. We now find the lowest cost edge which connects the 2 trees. The edge CD is respectively chosen. Figure 3 is the MST of the graph. This is a pseudocode for Boruvka's algorithm. The algorithm starts by taking an input of a graph G. Initially, each vertex in G is treated as a tree and placed in the forest T. These trees are referred to as individual components. On line 2, the while loop is executed under the condition that there is more than one component present in T. When T contains one tree, the while loop is not executed as this tree is the MST. Within the while loop, the for loop on line 3 goes through each component in T and creates an empty set. Furthermore, within this for loop, on line 5, we iterate over each vertex V in the component and find the least weight edge from V to a vertex outside of the component. This edge is added to S. We ensure the edge goes to a vertex which is not a member of the component C to avoid the creation of cycles. Upon the completion of the for loop on line 5, we analyze the set S and add the cheapest edge to T to combine the trees in the forest. This procedure is repeated until there is only one component. This is the MST. I will now demonstrate my Java program with the following graph G. My program is split into 4 classes. The graph class and edge class conceptually contain information required to represent the input and output graph. The driver class is where the algorithm is executed. The Boruvka class implements Boruvka's algorithm in the calculate MST function, which takes input of a graph. In this function, we see the pseudocode that was previously mentioned being implemented. The while loop on line 24 is executed under the condition that there is more than one component present in the forest. The for loop on line 32 iterates over the components, finding the cheapest edges. The for loop on line 54 adds the cheapest edges found to the minimum spanning tree. Now let's run the program with the example in the slide. As you can see, the edges 0 to 3, 0 to 1, and 2 to 3 have been correctly used to give an MST with a total weight of 19. There are several uses for Boruvka's algorithm. For example, if an electrical distribution company wanted to lay cables, they could use Boruvka's algorithm to find the shortest route around target locations to build a more efficient network. The algorithm has also been applied to NP-hard optimization problems, such as the traveling salesman problem. Boruvka's algorithm has changed the world, as it was the first algorithm to solve the MST problem, and led the way for other successful algorithms such as prims and Kruskal's. Thank you for watching.